Good morning, students. We'll move on to the second chapter of automata theory and computability. So we'll discuss machine-based hierarchy of language classes. So from this topic, we'll be getting a knowledge about how many different languages are available, which can be accepted by different formats of our machine. Fine. So here we are going to discuss about three different types of machine. One is the basic version, FSM we call it as finite state machine or finite automata also we used to call. Fine. This is the basic version of a computing machine which used to accept the string or else it will reject the string. Fine. Okay. So if the language is a bit complicated, we will be going to add a stack for the FSM, and this version we are calling it as push down automata. Fine. For FSM, if you are adding a stack, then it will be called as push down automata. Fine. Okay. Other than this, we have one more version of a machine that we are calling it as Turing machine, which is having ability to accept all the varieties of language. Fine. Okay. So now we'll go through what are the different types of languages are available. Okay. You can see first one is regular language, second one context-free language, third one decidable language, and fourth one semi-decidable language. Fine. In module number 1 and module number 2, we'll be discussing about regular language. In module number 2, we'll be discussing, in module number 3, we'll be discussing about context-free language. Okay. In module number 4 and module number 5, we'll be discussing about the Turing machine. Okay. Where decidable language and semi-decidable language can be discussed over there. Okay. Then, what is this regular language means? Fine. The regular languages are accepted by FSM. The language which is accepted by your basic version of a machine, which we are calling it as finite state machine. Okay, that particular language we are calling it as regular languages. Okay, so what will be the behavior of your FSM once it receives a regular language? The FSM starts from a start state and accept one character at a time. Fine. And changes the state based on current state and current input symbol. So remember, students, whenever we provide an input using a regular language to any finite state machine, so from where we are going to begin our computation, okay, your finite state machine will begin with a start state. Remember this. Okay, FSM consists of lot of states available. Fine. So out of that, one we are considering it as a final state. Okay, and more than one also we can have a final state over there. Sorry, like we are beginning with the start state. Fine, only one start state will be available. Okay, but we may have more than one final states available over there. So between the start and final, it depends on a string, or it depends on a like input. Okay, how many states we are going to involve. Fine. Out of our machine, you consider like 10 different states are available by default. Okay, according to my string, okay, according to any particular string or else regular language. Fine. If I want to provide it as an input, okay, it depends like how many states can be utilized out of 10 over there. Clear? Out of the 10, one will be made as a start, okay, and one will be made as final. Okay, it is not compulsory like only one should be made as a final. Okay, we have an option of multiple final state, but the start state should be only one. Fine. When we solve the problem over regular language, you'll be having better knowledge about what exactly this FSM stand for. Fine. Okay. After scanning the entire string, okay, if the machine is in a final state, then the string is accepted by the machine, or else it will be rejected. What is this exactly? Example of my name, okay, Prasad, which consists of total how many characters? Total 6 different characters is available. Okay, so consider we have a machine which is having total 6 different states to handle each and every character. 6 characters I have. Okay, so 6 different states are available. Okay, it is not compulsory like how many characters we are involving in our string. Same number of states should be involved from the FSM also. Okay, it depends on what kind of character we are using. Okay, that we will see later. For time being, just consider like, yes, we have a string which is called as Prasad. Okay, so which consists of 6 different characters. Now it should be either accepted by the machine or rejected by the machine. Fine. Now, according to my example, 6 characters, 6 different state. Okay, out of that 6, one will be start and one will be the final. Remember this. Fine. So now, after scanning, like first P will be scanned, then R will be scanned, like that. It continues till D. Okay. So when I reach my last character of my name, okay, Prasad, last character is what? D. When I start scanning the last character, then the machine should be there in a final state. Okay, how it will go for final state, you may ask. Okay, from start state to final state, how it will travel. Okay, that we will discuss. Okay, that we will discuss how it will change the, we are calling it as a transition. We call it as transition, change of state, or else change of state from one to another. Okay, by receiving a string, we call it as what? Transition. It's very simple. Okay, don't worry about that. So when I reach a last character of a string, okay, if the machine is in a final state, then the machine will accept the string exactly. Otherwise, it is going to reject the particular string. Why it is going to reject? Because the logic what I had designed for accepting the string mismatch. Okay, there may be error in my design itself, or there may be error in a string pattern what your machine is expecting. There are two possibilities are there. Clear? Fine. Okay, fine. The language accepted by finite state machine is called regular language. Okay, so this is about some brief introduction about regular language. Then the second version, context free language. Okay, so in regular language we got some kind of a restrictions over there. Okay, we'll see that what are those restrictions and all when we go for in-depth topic regarding the regular language and context free languages over there. Okay, so few flexibility is included in this context free language. The name only indicates context free. Okay, like we don't have a limitation, much limitation over here. Okay, we don't have much limitation over here. Because of that, the language what we can design, or the string pattern what we can design, okay, become more complicated. Okay, by using FSM we cannot compute these kind of strings. Okay, the complicated version of, or else context free language kind of a string cannot be processed by your FSM. So what we need to do, we need to go for adding small changes, or we need to include some changes for this FSM. What is that? Okay, we need to go for a advanced kind of FSM that we call it as push down automata. Okay, that we call it as push down automata. See, you can observe the first point. The context free language are accepted by push down automata. PDA we call it as. In your exam, they don't mention like push down automata. They're going to mention like PDA. That's it. Okay, PDA stands for what? Push down automata. Okay, what kind of language is accepted by push down automata? Context free language. Remember, FSM cannot accept context free language. Like that, PDA cannot accept regular language also. Remember, okay, vice versa. Fine, PDA is dedicated for context free language. FSM is dedicated for regular language over there. Okay, fine. Next point. For non-regular languages, okay, it is not possible to construct FSM. Okay, so what we do, we add a stack to FSM so that it can remember some symbols by pushing onto the stack. Okay, so here we need to deal about a lot of string values over here. Okay, it will be having a bit complicated version like a to the power of n, b to the power of n, c to the power of n. Okay, such kind of inputs string we used to get over here. Okay, so FSM cannot handle these kind of inputs, remember. Okay, so what we do, we are trying to push some value for a stack. Okay, from stack we are trying to utilize it for the computation. Okay, so this alternate procedure or some alternate arrangement, whatever we are doing, that we are calling it as push down automata. Why we are calling it as push down? Because we are using a stack. Okay, we are using a stack. Based on the behavior of this stack, we are naming it as what? Push down automata. That's it. Okay, nothing else. Okay, working and all will be much similar. Don't worry. Okay, then later, the FSM with stack is called PDA. Remember this. FSM with a facility of stack. Okay, we are calling it as PDA. Then PDA are used to accept only the non-regular languages such as context-free language. This is very, very important topic, non-regular language. Okay, you may expect around 6 marks question, one sure 6 marks question based on pumping lemma theorem. Okay, there is a theorem called as pumping lemma theorem. Okay, using which we need to decide whether the language is regular or not. Clear? This is very, very important. See the difference. If the language is regular, then FSM you need to design, right? If the language is non-regular, then PDA we need to design. Remember this. Okay, this is very, very important. This we will discuss, like pumping lemma theorem and all we will discuss in module number 3 exactly. Fine? Okay. Then decidable language and semi-decidable language. Okay, for time being, we will have just a glance. Okay, because this is not the situation, or this is not the time to discuss about this decidable language and semi-decidable language. Okay, but we will go through some basic concepts over here. Okay, so fine. Decidable language means what? For non-context free language such as a to the power of n, b to the power of n, c to the power of n, it is not possible to construct a PDA. Okay, so here also we are mentioning like what FSM cannot compute, that can be computed by PDA. What PDA cannot compute, that can be computed by someone else. Who is that someone? Okay, we'll see that. Okay, in such situation we go for a Turing machine. In such situation we go for a Turing machine. Okay, the working principle of Turing machine and PDA is much similar. Okay, so in case of PDA we are using a stack, that's it. Okay, but in case of Turing machine we are using something called as a tape, using which we are going to handle these kind of strings. Okay, using which we are able to handle these kind of strings. Okay, working principle are much similar. Okay, only few like additional like properties are added. Okay, in PDA and Turing machine. So that's it. Okay, then Turing machine can accept all type of language, including regular language and context free language. This is very important. Okay, your Turing machine is able to accept regular language, context free language, decidable language, and also semi-decidable language. Remember this. Fine. Okay, you may ask like why we need to go for FSM and PDA. Okay, why can't we go for direct Turing machine? Okay, because we need to understand what is regular language, how it can be handled by your machine, then what is CFL. Okay, then how it can be accepted or rejected by your push down automata, that we need to learn first. Okay, the basic question we need to learn, then we need to go for the advanced kind. Yeah, then decidable languages are decided by some Turing machine that always halts. Okay, like decidable means the name only indicates, okay, either yes or no. Okay, we can decide yes, okay, this is what, okay, or else no, this is not. Okay, such kind of decision we can take, okay, based on the Turing machine. Okay, so if that is like complete decision, if you are able to do, then we call it as decidable language using Turing machine. Remember. Okay, then if you are able to do some partial kind of decision, okay, then that will be considered as what? Semi-decidable languages. That will be called as semi-decidable languages. Okay, so here the languages which are semi-decidable by some Turing machine, okay, that halts on all string in the language. Okay, so whatever the string we get, your Turing machine should halt, okay, and it should process. Okay, it should not skip any character. Remember this. Fine. Okay, so this is what some brief introduction about how many different types of machine languages are available. Okay, so these are the 4 different languages. First one regular language, second one context free language, third one decidable language, and fourth one semi-decidable language. Okay, so we will move on to the next topic, functions on languages and programs. Okay, so here we need to discuss about one particular function, okay, that we call it as chop. Okay, you can observe. Okay, the name only indicates what? Functions on languages and programs. Okay, functions on languages. Okay, this is very important. Functions on languages. So this is what a function. Okay, what is the input for this particular function? The language will be provided as a function. Okay, complete language should be provided as a input for this function. What is this chop? Okay, so this definition is a bit confusing. Okay, whatever they had given in your textbook, just observe. The chop L is set of odd length strings, okay, obtained after removing or deleting the middle character. Okay, so this states that whatever the language we are having, okay, out of that the middle one should be removed. Okay, so later whatever we get, that will be considered as a result of a chop of that language. Okay, but what is this odd length? It's a set of odd length strings obtained after. Okay, you may feel like after removing we should get a odd length kind of language over here. No, this is wrong. Okay, just observe. Okay, just we need to make some little changes in our definition. Okay, see chop L or else a chop of a language function can be implemented over a such a string, okay, which is already having a odd length. Remember, which is already having a odd length in its language. Over that we can apply the chop L function. What we need to do, okay, over a odd length of a string, okay, we need to identify the middle one and we need to remove or delete. Okay, we need to remove or delete that particular character. Then whatever the value we are left with, okay, that will be the result of chopel. Clear? Okay, here we got one example, two examples. Okay, just observe. So here we got one language which is equal to a to the power of n and b to the power of n. Okay, a to the power of n, b to the power of n. N value may be greater than or equal to 0. We can begin with 0. Okay, we'll see that whatever the value we can get. Fine. Okay, so n value, if I take 0, just observe, when n is 0, then L will be equal to epsilon, empty string it is. Okay, it will be empty string, a to the power of 0, b to the power of 0, empty string we can consider, right? Okay, fine. Then what is the length of this particular language? 0 exactly. If you are having, when we were discussing about cardinality of a language, okay, then it states that what is the size of that particular language. Okay, so the length was epsilon, length for epsilon was what? 0 exactly, right? Okay, so same we are mentioning, length of epsilon will be 0. Okay, then later if I increment n by 1, if I substitute n is equal to 1, what is the value we are going to get? A to the power of 1, b to the power of 1, right? What is the length? 2 we are getting. Then if I substitute 2, then AA, BB we are going to get. What is the length? 4 we are getting. If I mention n value is equal to 3, okay, what is the length of the L we are going to get? Triple A, triple B. What is the length of that particular language? We are going to get 6. Is it? Okay. So now just observe, are you able to generate, okay, are you able to generate any odd value over here for any values of n? Can we? No. Okay, if that is the case, we are not able to execute the chop function. Why? Because we are expecting odd. Okay, when you elaborate the language string length should be what? Odd. Clear? Okay, but for this particular language, we are unable to generate the length of odd. Okay, so what we need to do? We cannot apply the chop function for this particular language. Clear? Okay, fine. So now we'll go for one more example. Okay, just observe, finding chop L, where L is equal to a to the power of n, b to the power of n, c to the power of n, right? Okay, so n value is greater than or equal to 0. Okay, for this example, we'll see whether we are able to generate odd length kind of a string or what. Okay, so if I substitute n value as 0, fine. If I substitute n value as 0, then epsilon we get. What is the length? Length will be even 0. Okay, can be considered as even exactly. Then if I substitute, just observe, if I substitute n value as 1, okay, then what is the outcome we are going to get? A, B, C we used to get. What is the length of this particular string ABC? 3. Yes, we are able to generate the odd length. Then chop ABC or else chop L also we can write. Okay, chop ABC or chop L. Okay, with a value of n is equal to 1. Then what will be the result? AC we used to get. See, the odd length, whatever we are going to get out of that middle one, okay, should be removed or deleted. Okay, so after the chop function, what you are going to left with? You will be left with AC. B got eliminated. Now, when n value is equal to 2, then a to the power of 2, b to the power of 2, c to the power of 2. Double A, double B, double C. What is the length? 2, 4, 6. No, we cannot apply a chop function because we are expecting a odd length of string over here, right? Okay, then if I substitute, so chop function cannot be applied for n value is equal to 2. for this particular string, right? Okay, then what about for 3? Triple A, triple B, triple C. Total, what is the length of this particular string? 9. Yes, it is a odd length. So what we can do, we can eliminate 1B. See here, we can eliminate 1B. He is the middle one, right? Okay, he is the middle one. See, 1, 2, 3, 4. 1, 2, 3, 4. So if you chop this particular string, then what you will be left with? Triple A, double B, triple C over here. Like that, we are having for a to the power of 5, b to the power of 5, and c to the power of 5 also. Okay. From this example, we can observe that whenever we are able to generate, remember this, whenever we are able to generate odd length string, then only we are able to apply the chop function for that particular language. Clear? I hope you don't have any doubts. Okay, so next, we'll move on to the next topic, very important, finite state machine. Okay, in short form, we call it as FSM. We'll see that what is the working principle of finite state machine, what are the different components are involved in this FSM concept. Okay, so finite state machine is a computing device which accepts a string as input and produces the output, accept or reject. FSM is also known as finite automaton. Okay, remember finite automaton. Automaton stands for machine. Okay, in case of Greek word, automata means what? Machine, exactly. Fine. So the definition of FSM is what? It is a computing device which accepts the string as input and produces the output, accept or reject. Okay, fine. So this is what a block diagram of FSM we got over here. Just some. Okay. So here there are 3 components. One is what the input, and second one is what the control unit, and third one is what the output unit. Okay. So output unit responsibility is like it need to check when we reach the end of this particular input string whether this machine is in, or whether the control unit is in final state or what. If this control state is in final state, or the control unit is in final state, and when we reach the input string, the last one, okay, then the output will be generated as accepted, otherwise rejected. Okay, so this is what the responsibilities of output unit. Okay, then what is the responsibilities of input unit? Okay, so it consists of input strings. So this is what the place where we are managing, or where we are holding our input string, which should be provided as an input for a control unit, okay, of FSM. Okay, so this is what the pointer, okay, this is what the pointer which will be pointing for the initial portion or initial value. Okay, then after reading each and every value, it will be incremented and it will be pointing for the next. Okay, when we reach the end of the portion, okay, and if your machine is in final state, then output will generate accept over there. Okay, so this is what the job, output over, input over. Now what about the control unit? Just observe, it look like a clock, right? 12, 1, 2, 3, 4, 5, 6, like that it continues, right? Okay, it look like a clock. So here inside this control unit, we got many number of different number of states. Okay, so these Q0, Q1, Q2 to Q7, whatever we have, this we are calling it as number of states. Clear? Out of this, one will be considered as a start state, and more than one we can consider it as final state over here. It depends on a input string, remember. Okay, like in FSM also there are 3 varieties, DFA, NFA and epsilon NFA. So when we discuss about that, you will be having better knowledge like how many different final states we can have. Clear? Okay, fine. So now in this example, just observe, we have some discussion over here. Okay, input. Okay, this string to be processed is stored in input. Okay, so whatever the string we want to process, like Prasad was my name, right? That was my example. Okay, so the Prasad will be uploaded in this input location. Then what about the job of control unit? Okay, it consists of a number of states. Okay, fine, number of states we have. The states are identified by Q0, Q1, okay, till Qn. Okay, so that is what the identification of state. Initially, the machine will be in start state Q0. Okay, remember always, okay, in our entire syllabus, Q0 we are considering it as a start state. Okay, Q0 will be considered as a start state, and final state, it depends on a string. Sometimes Q0 may be the final state. Start state and final state both can be Q0 itself. Sometimes Q1 may be the final state. Okay, it depends on the input what we are trying to process. Clear? Okay. And then machine will have at least one final state, at least one final state. See, in your exam, in previous year exam, like in 2019 question paper, okay, they made one mistake. Okay, they had given some finite state machine kind of problem, and they were unable to mention the final state. Okay, so they got complete grace marks over there. Without final state, we cannot proceed. Remember, okay, without final state, we cannot proceed. At least one final state is must and should. Remember this. Remember this. Okay, so if you are trying to design a FSM with a proper logic, and if you forget to mention the final state, you will get 0 marks. I repeat, you will get 0 marks. Clear? Clear? Final state is very, very important. Okay, at least one final state should be available. Okay, then based on the current input symbol and the current state of the machine, it may change its state. You may ask, okay, how it will travel from start state to final state. See here, Q0 is the start state, consider it as a start state, and Q4, which is I'm mentioning it as final state. So if I want to travel from Q0 to Q1, I need to travel to Q1, Q1 to Q2, Q2 to Q3, Q3 to Q4 exactly. So this is what the format, okay, of the transition over there. Okay, so whenever we get some input for a particular state, remember, whenever we get a input for a particular state, based on the input state and based on the input string or input character, the Q0 or else the state will decide whether it should go for the next state or whether it should remain in the same state. Remember this. Okay, how and why it will be, we'll discuss when we are solving the problem over there. Clear? Okay, fine. Then output, when end of input is encountered, and if the machine is in final state, then the input string is accepted by the machine. If not, machine will reject the output, it will reject the input string. So whenever we are reaching the final state, if I consider it as a final state, yes, I reached the final state and I also reached the end of this string. Okay, then your output unit will generate accept. Okay, otherwise, when I reach the end of this string, okay, consider like this is what the final state, but still you are in the Q3 itself. Okay, when I reach the final last input symbol of a string, okay, but still if I am available in non-final state, that is Q3, then the result will be what? Rejected. Yeah, so that is what few topic about, or else the basic of finite state machine block diagram. Okay, fine. So then we will use some notations over here. Okay, if I want to represent the FSM, okay, we call it a skeleton. Okay, using these varieties of symbols, okay, we are trying to represent. Okay, we are trying to represent the FSM. Okay, so these symbols we are using to represent the FSM. Fine. Okay, if you are designing the FSM with these symbols, then the complete FSM, we are calling it as skeleton. Okay, skeleton of FSM, we call it as. Okay, so we have some meaning, particular meaning over here. Okay, how we were having symbols in algorithm. Okay, it having some their own meaning over there. Okay, same kind we have over here also. Okay, so we'll see that different symbols are available. Okay, so this is what one symbol. See here, Q0. These are the states, nothing but states. Okay, Q0 with circle, one circle. Remember, we have a difference. Q0 with one circle. Okay, and it is having an arrow mark. Observe here, it is having an arrow mark. Okay, but we don't have any origin over here, right? Then this symbol we call it as a start symbol. Anywhere you find this kind of pattern in your question paper or anywhere, that indicates what? Sorry, not this symbol word. Okay, only this particular. Okay, Q0 with arrow mark, or else any particular state name, Q1 it may be, Q2 it may be, it depends. Okay, arrow mark with no origin, we call it as a start symbol. Remember, see here, a circle with an arrow which is not originated from any node, okay, represents the start state of machine. Then later, a state with double circle, we call it as a final state. Okay, see, two circles are used to represent a final state. Here, Q0 is the final state. Okay, depends. Remember, okay, I told you like Q0 should be the initial one. Okay, that's the start state. Okay, so you don't ask like why we are placing a double circle for this Q0. Okay, so it depends on a question. Okay, Q0, obviously it is a final state. Okay, but if I want, I can make it as Q0 is a start state. Fine. If I want, I can make it as final state also. It depends on a question. Okay, we'll see like what are the different kinds of questions are available. Okay, fine. Then later, so here we got the next variety or the next version. So here two different examples we saw, okay, where only one state was available, but here two different states are available, q0 and q1. Okay, so both are the states because it is in a circle. Fine. Then between this we have some arrow mark over here, right? Okay, and we are labeling it as one. This we are calling it as a arrow mark. The transition arc, we call it as arc, arrow. Okay, between one state to another state, we call it as a transition. Okay, this means, okay, I tell you the meaning of this particular transition. Okay, q0 is a present state. Fine. When it receive a input called as 1, it will change its state from q0 to q1. It means like this. Okay, your machine is in a state called as q0. Okay, fine. Let it be a start state. I will make it as a start by providing an arrow over here. Okay, q0 is a start state. Okay, so if your q0 receive a input called as 1, what it need to do? It need to change its state from q0 to q1 exactly. That is what it is stating. Okay, fine. So discussion we have over here, explanation. Okay, then symbolically how we can write, this is what the version. Okay, lowercase delta we are using. Okay, so this is what the transition function we call it as, lowercase delta. So in our every problem we need to mention these kind of transition based on this kind of skeleton. Okay, so understand this properly now itself. So lowercase delta is the transition function we are using. So this is what a function, open bracket. So here we are having two parameters. Okay, what are those? One is q0. See, present state should be first. Okay, where you are exactly? We are in q0 exactly, right? So what is the input you received? 1 is the input you received. Okay, then what you want to do? You want to change the state to where? q1. So that is what it state. Clear? Okay, fine. Now, one more example we are having. Just observe. Q0 is a particular state. Okay, fine. Let me make it as start state. Okay, now it is start state. Same variety. Okay. Now, instead of changing its state when it received the input, how we discussed in this example, what your Q0 is performing. Okay, it is remaining in its state itself. Okay, like this is like whenever Q0 receives 0, it won't change the state. Okay, it won't have a transition to another state. Okay, it will remain in its state itself. Okay, so we call these kind of symbol as self loop. Okay, or else self transition, we call it as self transition. Okay, so for few input, yes, we need to remain in the same state. Okay, so how we can mention this using a transition function, we'll see this. So delta is a transition function where you are exactly now in the state. Q0 is the state. What is the input you received? 0. Okay, so what is the outcome of this particular transition? Means we are remaining in Q0 itself, but here change of state it was, so we are mentioning it as Q1, but here we are not changing the state, that's why we left in Q0 itself. Okay, fine. Okay, next, one more variety of transition we are having, Q0 to Q1. So this states like Q0 will change its state from Q0 to Q1 if it receives 0 or 1. This comma represents 0 or 1. Okay, 0 comma 1 means 0 or 1 it is. Okay, see here an arrow labeled with 0 or 1 goes from state Q0 to state Q1. Okay, this indicates that the machine in state Q0 on reading is 0 or 1 enters into state Q1. Okay, this is represented as, see how we can represent using transition function. We'll see that delta of Q0 comma 0 1, okay, will be equal to Q1. Then later second delta of Q0 comma 1, okay, will be equal to Q1. Okay, means state Q0 on receiving 0, it will go for Q1, right? Or one more variety we are having, delta of Q0 comma 1, which is equal to Q1. See, all the possibilities of, remember, all the possibilities of transition function, or else all the possibilities of transition, whatever we may face, everything should be mentioned in case of this transition function. Remember this. Remember this. Okay. So then, last, what are the different types of finite state machines are available? There are three different types of finite state machine. Okay, DFA, NFA, and epsilon NFA, we call it as. Here, in this slide, we are mentioning it as DFA, means deterministic finite automata. Okay, non-deterministic finite automata. Then non-deterministic finite automata with epsilon most. Okay, like epsilon transition is also allowed in non-deterministic finite automata. Okay, then we are calling it as epsilon NFA. Okay, so in your exam or in the new syllabus, okay, we are naming this DFA as deterministic finite state machine, means DFSM. Okay, FSM. In case of finite automata, I told you right in the beginning of the finite state machine itself, I mentioned like we have another name called as finite automata for finite state machine, FSM. Okay, so this we can rename it as, okay, deterministic finite state machine, DFSM. Both are same. Okay, DFA is also same, DFSM is also same. FSM means finite state machine. Another name of this FSM will be what? Finite automata. Clear? Don't get confused. Like that, we are having three different varieties: deterministic finite automata, non-deterministic finite automata, then non-deterministic finite automata with epsilon modes. Okay, students. So this is of now. In next session, we'll discuss about deterministic finite automata. Okay, then later non-deterministic and epsilon NFA. Okay, so if you are done with these three discussion, module number 1 will be over. Thank you, students.